In this video we are going to talk about chords. Chord is a line segment drawn inside a circle. So you can see that AB here is a chord. A chord passing through the center is called as diameter. Now, there are a few things you should remember when you see a chord inside a circle. One of them is that when you draw a radius like that, OT, you have a right angle here. And what's more, OT bisects AB, meaning AM is equal to MB. This is very important because you will be using Pythagoras to work through those lengths, and when you find one of those lengths you can just double it to find the entire length of the chord. Another thing you should remember is Pythagoras. Now, you may not see Pythagoras here, but when you join A and O and B and O like that, you end up with right triangles in both sides. So obviously these are the radius, right? And what's more, this triangle AOP is an isosceles triangle because these are radii. And we said that these two are equal, so you should remember this when you see a chord inside a circle. Another thing you should see here is that this triangle could be drawn here on this side. Still, it's a little bit hard to draw with that. Let me go. I'm going to do it handmade like that. Yeah. So you may have an isosceles triangle on this side of the circle as well. Of course, these are not radius, so we don't know the exact length of this. It changes according to where you draw the chord. You could have it drawn here, you could have it drawn here, right? So what matters is that still this is an isosceles triangle and these are 90 degrees. So you should remember all these when you see a chord. Now let's look at this example. The diagram shows a radius OT, so this is the radius, that bisects the chord AB at M. Okay, so bisect means cut into two equal parts, so AM and MB are equal. MB is 12, okay, and so is AM. The radius of the circle is 13, so when you have the radius drawn anywhere, okay, and this one as well, these are all 13, so this is 13. Work out the length of MT. Well, you may get a little bit puzzled when they ask some line segment like that, but remember, you can always go with Pythagoras and work through those lengths. I'll draw this clearly. Now, we need this triangle so that we can find this length. To find this length, we need to find OM. So, I know that this is 13, I know that this is 12. So I can use Pythagoras to find this length and take away from the radius to find MT. So, I go like OM squared plus 12 squared equals 13 squared, as opposite to the right angle is hypotenuse, right? So I go OM squared plus 144 equals 169. From here I'll find OM squared to be 25, and I will end up with OM being 5 centimeters. Now that I know the radius is 13, I'll say it's not OT, it's MT equals 13 minus 5 which is 8 centimeters. So they can ask anything that you can find with Pythagoras. For example, the length of the chord AB is 16 centimeters, whereas OM here is 6 centimeters. So find the radius. Well, the radius is here. If you want, you can draw radius here, it doesn't matter. And you can use any of those right triangles you'd like. Now, you should remember here that OM bisects AB, so these are equal, hence you should have each one of these to be 8. So, taking this triangle, you can use Pythagoras, saying, let's say this is R squared equals 6 squared plus 8 squared. So you're going to find R squared to be 100, whereas taking the square root, you'll be finding R to be 10 centimeters. The question could well be like, find the measure of angle B, like measure of angle ABO. Well, you can do that because in this right triangle you know that this is 8, this is 6, so you can write down the tangent of that angle, let's say B now, equals 6 over 8. So you can go like the tangent inverse of 6 over 8 being the angle B. So you can find it. So basically what you need to remember is that you can always get a right triangle here by drawing the radius. When you have a right triangle, it is always Pythagoras there. To be able to use Pythagoras, you should remember that AB is bisected by OM, so these bits are the same. And just because you have an isosceles triangle here, you have the same angles. And if the figure goes that way, if you have this radius here, you can always have another isosceles triangle here where there are two more right triangles. So it's almost always about Pythagoras. Thank you. Now, solve the questions 5, 6 and 8 on your book and check your answers in the online self-check.